Hello. The topic of this lecture is on formalization into propositional logic and truth tables, which are a very important tool in propositional logic. I should mention here that the logic chapter in rationality is really good for describing why logic is important, describing some of its strengths and some of its limitations, and giving you a bit of a look at some of the tools that are used to make it work. But what it doesn't do is really give you a step-by-step guide for how to actually deploy logic in service of trying to figure out things like if an argument is valid or not. And that's the purpose of some of the other material in this particular unit, is to really teach you how to do that. So first, let's talk about formalization. The reason that we formalize things, that is, put them in this kind of shorthand or symbolic notation using these letters and the little words like and, or, not, if, then, is for the same reason that mathematicians use numbers and symbols instead of just spelling all that out in English. I mean, they could say 47 with the little hyphen in, or FORTY dash, SEVEN PLUS FIFTEEN. I mean, yeah, you could spell all that stuff out like, 47 plus 15, but it's much easier if you just use symbols for the numbers, and if you use symbols for plus, symbols for minus, etc., and all the other mathematical operations you could do. It's more compact on the page, it's easier to write down, it makes more sense visually, and we do the same thing in logic for the exact same reason. It's actually easier to work with that way. We can see facts about the structure of arguments that we couldn't see if we just left them in longhand English. And so one of the things to notice is that there are these little English words, and other languages, of course, have their equivalents of all of these words, but they're these little words that seem to have a logical function, and pretty much the only ones that we have to worry about are and, or, if, then, and not. At least until we get to categorical logic, which deals with all, some, and none. But between all those words, that gets at pretty much all of the logical relationships that are possible. It's kind of amazing. There aren't more, but you really can boil everything down to if, then, and, or, not, all, some, and none. I mean, that's pretty incredible, actually. But the idea is that in English or any language, you can connect things together with an and, you can connect things together with an or, you can connect them together with an if then, or you can modify them with a not. So let's take a look at some of these things one by one so that you can get some idea of how they work and some of the names for them. A conditional is what we call it when we use the if then. So any kind of an if then statement, we call that thing a conditional. And the if part and the then part also themselves have names, so more important vocabulary here. The if part of the conditional is called the antecedent. The then part of the conditional, is called the consequent. If you know Latin, that makes it much easier. If you don't, think of antecedent. It means in Latin the thing that walks before or behind, right? And so if you've heard the phrase the antebellum South, right, that is the South before the war. Bellum is Latin for war. Or if you have seen on a restaurant menu an antipasto salad, right, that's the salad before the pasta. So this ante or an I was going to say antecedent. That's exactly what we're looking for here. An antecedent is something that comes before. That word ante means before. And then consequent is something that comes after. So like the consequences for your actions happen after you act. And so you can sort of mentally think of it that way. It helps you maybe remember those terms. But they are fairly important terms because there's otherwise no way to refer to the if part of the conditional versus the then part. And those are the terms we're going to use. So for example, the phrase, if I have a boat, then I go out on the ocean, lyrics from a song, it's a conditional. I have a boat is the antecedent, that's the if part. I go out on the ocean then is the consequent of that conditional. Negation is where we use the not, okay? And I want you to notice that if you're looking at the truth conditions of something like the cat is on the mat and the cat is not on the mat, notice you're looking at the same thing. And that's really an interesting insight here. So the only difference between the cat is on the mat and the cat is not on the mat isn't what you're checking to see if they're true. It's just this little not here. And so in a weird way, this not is not really part of the sentence. It sort of modifies the sentence, right? And so either way, you're looking to see if the cat's on the mat. And if you've got this not in here, well, then if the cat is not on the mat, then you've said something true. And if the cat is on the mat, you've said something false. It just reverses the truth value of whatever it's present in. So we don't generally take those two sentences to be expressing two different different propositions. Both are talking about the proposition that the cat is on the mat. One of them is simply negating that proposition. And so one of the things that we're going to be using is what are called claim variables. Just like in mathematics, sometimes letters are used as variables for numbers or for numerical values. We can do the same thing, except use a lowercase letter to stand for a whole sentence. And again, the reason that you do it in math and the reason that you're going to do it here in logic is the same reason, to make it a little easier to write down, to save a lot of space, to save time and paper, and to be able to just generalize. So we're not talking about a specific sentence, we're talking about any old sentence that could fit into that slot. So any sentence that makes a single claim can be substituted with a lowercase letter to save time and paper. It becomes what we call a claim variable. So we would write some conditional as if P then Q, where P and Q stand for any two complete claims. That is, something that says something about something, like the cat is on the mat or the moon is made of cheese, etc. Similarly, we can write a negation as not P, where P is any complete claim. And so you can write the word not and then P, and you say, look, not P is the opposite of P, whatever P is. And so P just gets to stand for some sentence, something that says something about something. The English word and is often a way to connect two claims. So we can put a sentence in the first blank and a sentence in the second blank, or a lowercase letter if we're going to use claim variables. And so instead of saying something like, I am wearing a hat and I am wearing shoes, we could simplify that down to something like P and Q, because there's two sentences, right? Two things that say something about something, and we're connecting them together with an and. We also sometimes use the word or as another way to connect two claims. You can say, one thing or the other thing is the case, right? So one thing is the case or something else is the case. So either way, a full sentence has to go into those blanks that are there, but that's what gets connected with an or. So let's talk a little bit more about conjunctions. The sentence, I am wearing a hat and shoes, expresses two claims. It expresses the claim that I am wearing a hat, it expresses the claim that I am wearing shoes, and it connects them together with an and. You can see the and right here. So the phrase A and B expresses I am wearing a hat and shoes. It just substitutes the first claim with an A, substitutes the second claim with a B, and now it can just generalize. Any old conjunction looks like A and B. So notice that since I'm wearing shoes and a hat means the same thing as the above, that means A and B expresses the same thing as B and A. So the order with an and doesn't really matter. It does with a conditional, but it doesn't really with a conjunction. So before you get to thinking that this is too awfully simple, well, of course, there are always complications. It's important to note that our natural language is a lot more rich and varied than this sort of symbolic language that we're going to be teaching you here. Not all instances of the English word and are logical conjunctions. That is, not every time we use the word and do we use it to connect together two complete sentences. Right? That's just not always how we use the word. So for example, in the sentence, the priest married John and Joan, is not saying the priest married John and the priest married Joan. I'll leave it to you to consider how many different violations of the ecclesiastical order that might represent. So the word, the and in there, John and Joan, is meant just to say, okay, no, these are two individuals that come as like a unit for this case. So that's the priest married John and Joan is one thing that could be true or false. On the other side of things, not all logical conjunctions even use the word and. They sometimes use a different word, but they are a logical conjunction. So for example, in the sentence, that ring is beautiful but expensive. That is actually saying two separate things. It is saying the ring is beautiful and the ring is expensive. And so again, it doesn't use the English word and, but it's absolutely a conjunction because it asserts two things at the same time. That's what an and does. Let's talk a little bit about disjunctions now. So for example, the sentence, people put cream or sugar in their coffee. That expresses two claims. It expresses that people put cream in their coffee, and it expresses the claim people put sugar in their coffee, but it connects them together with an or, right? When you say one thing and another, you're saying both of those things are the case. That's what you're asserting. With the or, you're saying it's one or the other. It's like one of those things is the case, is all you're saying. And so notice that those claims are also not exclusive. That is, some people put both cream and sugar in their coffee, and that doesn't make the sentence false, right? So the fact that some people use both doesn't mean it's false that people put cream or sugar in their coffee. No. Both is okay. That's called an inclusive or, and that's going to be the default. We're going to generally treat an or as inclusive unless we specify otherwise. And so again, if we're going to symbolize that, sort of abbreviate it, we're going to use this phrase here, C or S. And again, you could pick any letter you want. In this case, it's just pretty clear what stands for what. And so again, this could stand for any sentence though. So this is what any old disjunction looks like. It looks like C or S, where C and S are sentences, things that say something about something. And again, note that because people put sugar or cream in their coffee means the same thing as people put cream or sugar in their coffee. S or C means the same thing as C or S. There's, again, direction doesn't matter for the or, just like it doesn't matter for the and. And I mentioned this on the last slide, but we'll mention it more specifically here, this notion of inclusivity, right? And so consider the sentence, you can order a hot dog or a hamburger at Freddy's. The fact that you can order both a hot dog and a hamburger at Freddy's, I don't actually remember which combo number that is, but that doesn't make the sentence false, okay? So often when we see an or, we tend to want to interpret it as being exclusive, and we should not do that automatically. In logic, the or is going to be by default an inclusive or. That means one or the other or both. Right? It would only be false if you could order neither a hamburger nor a hot dog at Freddy's. So consider the sentence, you could use a blue marker or one of a different color. Well, notice you can't actually use both a blue marker and one of a different color at the same time. Those things are mutually exclusive. And so this use of or in English really is exclusive. And so notice that the exclusivity is due to the content of that sentence, not the structure. When we just see a plain old or, we're going to assume it's inclusive unless there's some reason why we can't. And because logic only looks at the structure of the language, we're going to always interpret this or as being inclusive. If you want to express an exclusive disjunction in our logical speak with our abbreviations and everything, you would say something like A or B and not A and B. That is one or the other and not both. Okay, now for some examples of how to turn ordinary English language sentences into the sort of shorthand symbolic language that you're going to want to use. So consider the sentence, Fred had pie and ice cream for dessert. So if you're noticing that there's the word and in there, that's good, right? You're looking for those little logical connective words. In this case, though, you want to make sure to take a step back and say, all right, is that and connecting two different sentences, like two whole things that could be true about the world? So is it the case that Fred had pie for dessert and he had ice cream for dessert? Did he have two desserts? Or did he have one dessert that consisted of pie and ice cream? I mean, I guess you could interpret it both ways, but the more natural interpretation is to say Fred had one dessert that was pie and ice cream. And so that and is not connecting two complete independent sentences. And so it's just a single sentence. It says one thing about the world. So Fred had pie and ice cream, right, for dessert. That's one thing that about the world that could be true or could be not. Maybe he did have that, maybe he didn't. So that's just a lowercase letter. You could use A, you could use any other letter. That's fine. Okay. Now take a look at this one. It says, Susan speaks both French and English. Right. How many things does this say about the world? Again, you see that and in there. And so is it saying that Susan speaks French and Susan speaks English? Yes, that's exactly what it's saying. And so it's a plain old straightforward conjunction. It joins two sentences together with an and. The sentence that Susan speaks French and the sentence that Susan speaks English. Again, remember in those lowercase letters, you have to say something about something. Otherwise, that's the only way for something to be true or false. Okay. All right, let's take a look at the next one. All right. So it says someone who speaks both French and English is bilingual. This one's a little more complicated. This would involves, so I want you to maybe pause and really think about this and maybe write down a couple of ideas. And if you're looking at that and between French and English and thinking, that's got to have something to do with it, you're looking for those little logical connective words, and that's good. So what looks like it's going on here, okay, is saying something like if someone speaks French and someone speaks English, okay, then that someone is bilingual. So if one speaks French and one speaks English, then one is bilingual. And that seems to be the structure of what's going on there. So note the parentheses around the A and B here. The reason we put these parentheses there is because these things go together. The B doesn't go with so it's not if A and B then C, right? That's not what's going on here. It's if A and B, then C. And so that's what the parentheses help to do. They help to clarify that. If China doesn't win the event, then Croatia will. Again, take a minute, pause the video, write it down, and see how you do. So again, if you're looking at the if, right, there's an if here. There is a not. You shouldn't gloss over that. That's a negation. So if it is not the case that China wins the event, then, right, it's the other part of this if-then statement, then Croatia will, presumably means win the event. Okay. So that's going to look like if not A. So if China does not win the event, then B, Croatia will win the event, right? And so that's a conditional, and the antecedent of that conditional is a negation. Okay. Again, note the use of the parentheses to keep the difference between if not A, then B, and not if A, then B. You want to make sure to put those all in the right organization. Speaking of the right organization, that's what's important with an example like this one. And again, go ahead and pause it and take a try a little bit of practice here. This one says Biff wants a steak or soup and a sandwich. This is actually a little bit ambiguous in English, but it's fairly clear what it means. So the question is, does he want steak or soup? And he's going to have a sandwich no matter what, right? So he's going to have a sandwich and he's deciding whether to have the steak with the sandwich or soup with the sandwich. Probably not. It looks like in this, the most natural reading is that Biff wants a steak or soup and a sandwich. So think about that and think about the way the parentheses would go. And again, pause it for a minute and give it a shot. Okay, and that's what we're going to get here. We're going to get A or B and C. So he wants a steak or soup and a sandwich. So he's trying to decide between steak on the one hand or soup and a sandwich on the other hand, not steak or soup along with a sandwich, right? All right, now let's consider a little couple of review questions here. When you see a sentence like A and B, under what conditions would that sentence be true? Right, so it's a more complicated sentence than the cat is on the mat. Now imagine it's a conjunction, right? The cat is on the mat and the moon is made of cheese, right? Think under what conditions would that sentence be true? It's very important to remember that that kind of a sentence, a conjunction, is true when both A and B are both true and it's false otherwise. So if I say the cat is on the mat and the moon is made of cheese, I have said something false because the moon is not made of cheese, right? Now, even if the cat were on the mat, look, I said and, right? And that's the way and works. They have to both be true for the overall and claim to be true. And that makes sense. Again, that's how any competent user of the language uses the language, but it's important to realize that explicitly. So now consider the sentence A or B. Right? Under what conditions is something like that true? And again, if it helps, imagine some complete sentence in the place of A and a complete sentence in the place of B. But or, okay, an or claim, a disjunction, is false when both A and B are false, but true otherwise. That is, it's true as long as A is true or B is true or both. Right, so as long as one of them is true, at least one of them, then the or claim is true. How about not A? When is not A true? Well, it's true when A is false, and it's false when A is true, right? It's the negation of A. And then if A, then B. This is a little bit trickier to do intuitively, but basically what it means is it's false when A is true and B is false, and it's true otherwise. If there's something that bothers you a little bit about that, I would very much encourage you to talk to your instructor because it's a longer discussion than we're really going to have time to get into here. But for all other purposes, a conditional, an if-then statement is false when the antecedent is true and the consequent is false, and true otherwise. All right, the second section of this lecture concerns truth tables. That is, what are we supposed to do with our sentences once we have them all pared down, once we've revealed their structure, once we have just if, then, and, or, and not, and all that stuff is stripped away, and we've got that and those little claim variables, and we've got a nice little argument structure, essentially. Well, I'll show you what to do, and this is what's called a truth table. And so consider the following argument structure. We're going to try and ask whether the argument if P then Q, if Q then R, not R, therefore not P. We're going to see if that's true. You might be able to tell just by sort of looking at it, thinking very carefully about it, but chances are probably not, or you're not super sure about that. The nice thing about a truth table is it's a way of being completely certain about whether an argument is valid or not without having to do anything except follow rules, right? There's no judgment of any kind involved. Like if you follow the rules properly, you can do this truth table. Computers can do truth tables, right? And computers can't think at all. So you can do this as well. That's the great benefit of the system is that it allows you to find something out without having to actually think. All you have to do is be able to follow rules. Now, in order to follow the rules, you have to know what they are, but that's easy. Okay, so here are the steps to making a truth table. First thing to do is create the reference columns. If you'll notice on the previous argument, go rewind and look if you don't believe me or wanted to verify that, there are only 3 different claim variables. There's a P and a Q and an R, and some of them occur in more than one place, but there's just a P, a Q, and an R. And so your reference columns will have one lowercase letter for every lowercase letter that occurs in the argument that you're looking at. And so since we have just P, Q, and R, that's where we start. And then you also, in step 2, want to make one column for every individual instance of a connective that occurs in the argument. And so you want a column for the if-then, that is if P then Q. You want a column for the if-then, that is if Q then R. You want a column for the not, that is not R. And you want a column for the not, that is not P. So every connective, every instance of a connective gets its own column. Step 3, you want to fill in the reference columns. Now there's a certain logic to this, right? So I want you to look for a minute. Let me use the little pen here. I want you to look for a minute just at these boxes here. Right? So notice what this means is that R, any given sentence, has to either be true or false. Right? The world is either a certain way or it isn't. And if this sentence says something about something, well, either that's true or it isn't. Right? That's the only possibilities. Every claim is either true or false, never both, never neither. And so R can be true or R can be false. Once you're adding in another claim, a different claim, Q, well, now you all of a sudden have more possibilities. So the idea is that that Q could be true, right? Or Q could be false. And Q could be true while R is true, or Q could be true while R is false. Also, Q could be false while R is true, or Q could be false while R is false, right? And so, in a sense, that's what we're symbolizing with, with arranging things this way. So we have on the rightmost column, we have alternating true, false, but then we have true, true, false, false, because we have to account for Q being true while R is true or false, and Q being false while R is true or false, right? And that gives you, these 4 boxes here would give you every possibility if there was only 2 sentences. If there's 3 sentences, well, now you just have, okay, well, P could be true while all of that's going on, or you'll notice this box is the exact repeat of the above boxes. Right, so Q could be true while all that's going on, or P could be false while all that's going on. And if you just sort of keep doing it that way, so if you had 4 claims, we would have a table that is twice as long as this one. We would need 8 trues over here, and then 8 falses, and then we would sort of essentially repeat this box here for all the falses for, say, S, if we wanted to put that over here. And so that's the reason that this is filled out this way. You do this more or less just automatically. So true, false, true, false, true, false, true, false, true, true, false, false, true, true, false, false. And it just depends on how many claims you've got here. There's a formula for that. It's 2 to the n, where n is the number of claims you have. That's how many rows you'll need. Or you could just simply brute force it until you have all the possible combinations. If you do it this way, like in this exact order, then one thing that's nice is that everybody's truth tables will contain the same information on the same row. So everybody's row 1 will have the same information, everybody's row 2 will have the same information, everyone's row 3 will have the same information, etc. And that's nice. So there are some good reasons for doing it in a standard way like this. But those are the reference columns. Then the last thing to do is fill in the rest of the truth table. And what you do there is you look at the columns themselves, right? And what, so for example, this is a conditional. And so you will look at the antecedent of that conditional and the consequent of that conditional over here, right? So on the first line here, that P, the antecedent, is true. And the consequent is also true on that first row. So treat every row as if it's kind of its own little world. It's one way that things could have been, right, or could in fact be. And so if somebody says if P then Q, and in that situation P is true and Q is true, then, right, if P then Q will be true. So in fact, you'll notice that both of these first 2 rows contain the same information with respect to P and to Q. Remember, a conditional is false when the antecedent is true and the consequent is false, and true otherwise. So look here on the next row that we would have to take a look at. If P is true, the antecedent, and Q is false, remember, a conditional is false when the antecedent is true and the consequent is false. So actually that one's going to come out false. And so is the row right after it because it has the same information. So look at that. On the following lines, you'll notice that the antecedent is false and the consequent is true for the next two, and the antecedent and consequent are both false. Now remember, a conditional is false when the antecedent is true and the consequent is false, and it is true otherwise. Again, if this sort of bothers you or seems unintuitive, I would encourage you to talk to your instructor about that until it all makes sense and you're at least satisfied with that. If not, at the very least, remember that that's the rule and actually use it, whether it makes sense to you or not. Better that it makes sense, then you don't have to remember it, but at the very least, remember it. All right, so that fills in this whole first column, the column for if P then Q. We'll now turn our attention to the column for if Q then R. Now you can do a little bit of a shortcut on this. Notice that that is a conditional. Remember that conditionals are false when the antecedent is true and the consequent is false. So if you see places where Q, the antecedent, is true, and R, the consequent, is false, you'll notice that that applies to this line here, that second row. And you'll notice that that also applies here. And so what you can do is you can say, all right, well, those are cases in which, the only cases on this table in which the conditional comes out false, and that must mean it must be true in all of those other ones. And so it's false when the antecedent is true and the consequent is false, and true otherwise. And so we can just pop some truths into the rest of those tables. That helps you fill out a truth table a little bit more quickly. The nots are very easy. If you just look at R, it's going to be the opposite of not R. So if R is something true, then not R will be false. And if R is false, then saying not R would be saying something true. And so that's just how that works. Whatever R is, not R is the opposite. And so you just sort of flip from true to false there. And then you do the same thing with not P, right? You're using this operator not here, and it's operating on P, which is, this is the P column. Which is why you need to do your reference columns first, because otherwise then you don't have anything to put into the rest of these boxes. All right, and so that is a fully completed truth table. Now you want to say, all right, what's the point? Remember, we had an argument here, right? And the argument had this here as our first premise, and this was our second premise, and this was our third premise, and then this was the conclusion. We wanted to know whether that argument was actually valid. Now this is the point at which you want to pause and think to yourself, okay, what is the definition of validity? Right? And again, remember that sort of math book definition of validity, not the casual conversation definition. What is validity? And you want to say, all right, now how can I take that definition and look for what that would mean on a table like this one, where what we've done is we've said, here's all the possible ways that these things could have come out, right? This represents every logical possibility in the world. That's all sort of over here in the reference columns. And so, think to yourself, what would validity really mean? Remember the definition that an argument is valid if it is impossible for the conclusion to be false while the premises are true. Or in other words, if the premises are all true, then the conclusion must be. And since a truth table shows you every possibility, that's what you're looking for. You're looking for any row where the conclusion is false while the premises are all true. And so that's what we're going to do. We're going to look through the whole table and we're going to say, is there any place where the premises are all true? Well, okay, if we look at row 1 here, oh, there's, that premise 3 is false. So we don't, that row doesn't tell us anything one way or the other. Right? It just says that in some cases, the third premise is false. Well, here the second premise is false, right? Here the first premise. So we're looking for a place where they're all true, and that doesn't happen until we get this last row here, where each premise does end up true, and they end up true in the case where P is false, Q is false, and R is false. And notice in that one and only case where the premises are all true, well, then the conclusion is also true. And so that means that literally every time the premises are all true, the conclusion also must be, and so that means it's a valid argument. Now, I want to caution you, one common mistake that students make when first learning truth tables is that they will believe that if there's any line on which everything comes out true, it must be valid. That's not the case, okay? It's only if every time the premises come out true, the conclusion is true, that the argument is valid, right? If there was some other line where the premises were all true and the conclusion was false, it would be invalid, okay? If that ever happens, if it's ever the case where the premises are true and the conclusion is false, then it's an invalid argument, no matter how many lines come out where everything comes out true. Again, remember the definition of validity, treat it very precisely. So let's take a look at another completed truth table, this one for chain argument. So that's the argument that says if P then Q, if Q then R, therefore if P then R. And notice this one has a lot of cases where the premises are true at the same time. Part of that is just having, fewer premises, right? So there on that first row, both of the premises are true, right? And then here, right? And then here too, and here. And so the idea is that, again, there's a bunch of cases where the premises are both true. And what has to happen in order for this to be a valid argument, according to our definition, is that every time the premises are true, the conclusion would have to be, right? There's no cases where there's a false conclusion with true premises. And so that's a lot, but let's see what happens. So on that first row, there they are, okay? The premises really do seem to give you the conclusion on that line. They do on that line as well, and on this one, and on that one too. Okay, great. And so that means, again, it's not just because there is some line on which everything comes out true, it's that every time the premises are true, the conclusion ends up true as well. So let's show you another example. Here is an invalid argument. It's a very simple truth table, as you'll notice. Remember, this is affirming the consequent. That's the argument that where premise 1 is if A then B, and premise 2 is B, therefore A. If you say if A then B, B, therefore A. That's this argument. Okay, now notice there's only one, actually there are two places where the premises both turn out true, right? There, and here on this third row. Now notice on this first row, the premises, premise 1 and premise 2, end up having a true conclusion. You might say, oh, hey, that means the argument is valid. Not so fast. Here on the third row, the premises are true and the conclusion is false. If this ever happens on a table, that the premises all come out true on some row and the conclusion ends up false, that's what tells you the argument is not valid. Remember, the definition of validity is that it is impossible for the conclusion to be false while the premises are all true. And that's exactly what's being shown here. So if that's ever possible, which it is because there it is on the truth table, then the argument is invalid. So affirming the consequence is, as we know, invalid. So this is one of those things where this is a lot of very basic information. Of course, the text takes a lot more of a slow, more step-by-step explanation, but this also needs to, there's multiple modes to try and present the information. This kind of information is not the sort of thing that you can really just soak up passively. And so if it doesn't make perfect sense as to why everything has to be the way that it is, why everything has to work the way that it does, don't just wait until it makes sense months later. It's not going to. You have to actively try and understand this sort of stuff. And if something's not quite coming out, or if you're not able to predict what happens next or explain exactly why it has to happen next, then there's something you don't quite understand, and that's not uncommon, and that's not a problem. It's not like a moral failing or something. It means you're learning something. It's no big deal. But you do need to take extra steps to ask your instructor questions, because usually what happens is the trouble that students have with logic, it's one little thing that they just didn't quite, that they just sort of missed, or that they had just a little bit wrong in their head, and it's goofing everything else up. There's a lot of moving parts that all have to work right for you to be able to do logic, and your instructor will be able to figure out very quickly what might be a little goofed up if things aren't making as much sense as they should, and be able to get you corrected and sort of put on the right track. But again, that only happens if you ask. You are not going to automatically get this. You actually have to try and ask questions and correct misunderstandings that are very, very, very easy to get. Right, so that's a bit of very important advice, and we'll see you in the next lecture, which will be on categorical logic, a whole nother system of logic to deal with different kinds of claims and arguments.